Hello, grade 12. In today's lesson, we're going to be looking at electrochemical cells, and we are mainly focusing on galvanic cells. So without any further ado, let's have a look at this question 8 that we have here. So it says the electrochemical cell illustrated below is set up under standard conditions. And then as we can see here, this is our hydrogen gas. But since it is a gas, we know that we need an inert solid here that will take the place of the electrode. So we have our platinum, and this is the H plus ion in aqueous solution. And then here we have component X, which we know is the salt bridge. And then here we have our Mg2 plus ions, and then this is the Mg electrode. Now 8.1 says component X completes the circuit in the cell. State one other function of component X. So what is one other function of the salt bridge? So for 8.1, we say it ensures neutrality in the cell. Then we have 8.2, it says define the term anode. What is an anode? We say an anode is the electrode where oxidation takes place. So if you can remember, we have an ox. This means that in the anode, we have oxidation, and then we have red cat, which means in the cathode, we have reduction. So anode is simply the electrode where oxidation takes place. Then 8.3 says identify the anode in the cell above. So now that we know that the anode is the one that will undergo oxidation, we have to check between this, which one is the anode. But then there's no need for us to go to the table here. This is only a mark. So how will we know which one is the anode here? By simply looking at this one, we can see that there are bubbles forming. And then in terms of our knowledge of this galvanic cell, we know that where bubbles form, it is the cathode. So in the cathode, we have bubbles forming. And then we also have what? Increase in mass. So where we have an increase in mass and also bubbles forming there, that's the cathode, which simply means that the anode will have to be the Mg here. So our solution is Mg magnesium. Then 8.4 says write down the reduction half reaction that takes place in the cell. So the reduction half. So we know that reduction takes place where? In the cathode. So we've already identified that this side is the cathode here. So which one are we going to use? Are we going to use platinum or the hydrogen gas? It's obviously the hydrogen gas, because remember, platinum here is inert. So that means it's not reactive. Then we have the hydrogen gas there. So to write the reduction half of that one, we have to check exactly where we'll have our hydrogen, and then also producing the H plus ion. So we know that one has a reading of 0. So it is this one in bold. So because this is reduction half, we just simply write it as it is. And mind you, I'm using table 4b. So for galvanic cells, please use table 4b. Then we write it as it is, because remember, these are reduction. These are standard reduction potentials. So this is in the form of a reduction, right? So we can see a H plus here having an oxidation number of +1, but then when it becomes a diatomic molecule here, it has an oxidation number of 0. So what is happening? This is reduction, because reduction is simply the decrease in oxidation number, or it's where there is a gain of electrons. So from +1 to 0, that's a gain of electron. So a gain of electron is indicated by a decrease in oxidation number. So this is our reduction half reaction. Then 8.4.2 says name or formula of the reducing agent in the cell. So what is a reducing agent? Do not be confused. The reducing agent is one that undergoes oxidation. So this is a substance that will undergo oxidation, but then in the process, it reduces the other substance. It causes the other substance to gain electrons, right? So which one is the reducing agent? Obviously, we'd have to get the reducing agent in the anode side. So this one is the reducing agent, because as we can see here, there's an increase in oxidation number, meaning that it is undergoing oxidation. So an increase in oxidation number is oxidation. So from oxidation number of 0 to +2, that's an increase in oxidation number, indicating that oxidation took place, and therefore it is the reducing agent, magnesium. Then 8.5 says calculate the initial voltmeter reading of this cell under standard conditions, So, okay, let's calculate the initial reading. So we simply write E cell is equals to E cathode minus E anode, right? Now, we know using our table 4b, we simply say whatever that will be found above is the anode and whatever that will be found below is the cathode, right? So remember, what do we have? We have magnesium and hydrogen. So we can see that magnesium is up here, which still agrees that anode is magnesium here is the anode. So it has a reading of negative 2.36. So let's see, does it correspond to that? Yes, it's negative 2.36. And then we have our cathode. Our cathode has to be this one. In this case, it's the one that is below. So it has a reading of 0.00. So that means we have 0.00 minus negative 2.36. And this will give us 2.36 volts, right? So that's our E cell reading, our voltmeter reading. Then 8.6 says the Mg2 plus half cell is now replaced by the Cu2 plus half cell. So that means the magnesium electrode is now replaced by the copper electrode. It is found that the direction of electron flow changes, right? Then what are they saying here? Fully explain why there's a change in direction of electron flow by referring to the relative strengths of the reducing agents involved. So we want to see why there is a change in direction of electron flow when we replace the magnesium electrode with the copper electrode. Let's check now. The magnesium electrode was here acting as the anode, and then before, so this is before, this was the anode and this was the cathode. But then now check what is happening. As soon as we change this one, and then it becomes, we replace it with the copper. So we have to look for the copper that is correct. Remember, we are given Cu2 plus. There are so many coppers here. You can see there is copper here, copper Cu2 plus and Cu plus. We cannot take this one because it does not correspond with this one. It is not exactly the same as this one. Then you also have another one here, here Cu plus plus E, Cu. This is also not the one because it does not correspond with this one. Remember, this one, it actually loses 2 electrons, right? So now we want to choose the correct one. Which one is it? This one. This one is perfect here with a reading of 0.34. But can you see what is going on here? Now, since we replaced this one with the copper ion, that means this whole thing changes. The hydrogen electrode now is the anode because it is the one that is above. And then here we have this one now acting as the cathode. So you see now, remember, electron flow is always from the anode to the cathode. So initially we had electrons flowing from the magnesium electrode all the way to the hydrogen electrode. So it was from Mg to H2. But then now what is happening, because this one now acts as the anode, the hydrogen now will have it flowing from H2 to Cu, which is now the cathode. So what are we going to say in explaining that? We'll say H2 is a stronger reducing agent than the copper 2 plus ions, right? So H2 is a stronger reducing agent. What is a reducing agent? We've already said this is the one that undergoes oxidation. So in other words, the H2 is the one that will now undergo oxidation, right? Hence we say it's a stronger reducing agent. So H2 will now undergo oxidation. And then what will happen to the copper 2 plus ion? They will be reduced, right? That means they will gain, right? Reduction will take place. Cu2 plus will be reduced to Cu from a oxidation number of positive 2 to an oxidation number of 0. That's a decrease in oxidation number, meaning it is gaining electrons. It is being reduced, right? Thus now electrons will flow from H2 to Cu. So it always flow from the anode to the cathode, from the one that undergoes oxidation to the one that undergoes reduction. I hope all that makes sense. Okay, then we have 8.1. It says a piece of zinc is placed in a test tube containing an acidified permanganate solution, which is MnO4 minus. After some time, it is found that a redox reaction has taken place. Now, it says, use the table of standard reduction potentials to answer the following questions. First, it says, write down the name or formula of the reducing agent. Again, the reducing agent is the one that undergoes oxidation. It is very important that every time you are seeing this word, you remind yourself what is a reducing agent, what is an oxidizing agent. Because remember, it might get a little bit confusing to say that reducing agent is the one that undergoes oxidation, but oxidizing agent is the one that undergoes a reduction. So you have to be really careful with that. Now, write down the name or formula of the reducing agent. We are looking for the one that will oxidize between the zinc and the permanganate ion. So if we check here, we check our table, we have, let's see, where do we have our zinc here? So let's look for zinc. I think we have zinc somewhere here. So there we go. So zinc is negative 0.76, but then we want to check where do we have the permanganate ion. So we're looking for the permanganate. The permanganate is down here, right? So again, we know down is the cathode and up is the anode. And then using our NOx, we know that in the anode, that's where we have oxidation. So between zinc and permanganate, we can now clearly state that the one that is undergoing oxidation, the reducing agent, is of course zinc, right? Because it is being oxidized, right? So it is being oxidized to zinc 2+. Then 8.1.2 says, refer to the relative strengths of the oxidizing agents to explain why a redox reaction has taken place. So we want to refer in terms of the relative strengths. But remember, we've already said that zinc here is the one that undergoes oxidation, and then permanganate is the one, obviously, that will undergo reduction. So we can say zinc 2+ ion is a weaker oxidizing agent, right? So weaker oxidizing agent means that this one cannot reduce, right? It cannot reduce as much as the permanganate ion. So it's a weaker oxidizing agent. Remember, again, oxidizing agent undergoes reduction. So the zinc 2+ ion are a weaker oxidizing agent because they cannot reduce. They cannot they cannot gain electrons, right? Then than MnO4, then the permanganate ion. So the permanganate ion will be the one that will be reduced to Mn2+. But then now you might question this and say, how come something that has an oxidation number of -1 reduces? Remember, reduces means this gains electrons, or it says or it means that there will be a decrease in oxidation number. Now, this might be a little bit confusing because now you are looking at -1 and then you want to get to +2. It doesn't make sense that this is a decrease in oxidation number because as far as we are concerned, from -1 to +2, that's an increase. Now, you have to be very smart in answering this question here. This is not about the whole permanganate ion. It is really about the manganese here. So we are really looking at the oxidation number of manganese in the whole permanganate ion. So this is what we had as our exceptions in grade 11, whereby we said if we want to find the oxidation number of manganese in here, we'd say X. So let X indicate the oxidation number of manganese. And then now we know the oxidation number of oxygen is -2, but how many ions of that oxygen? We have 4. So it's 4 times -2. And then that is all equals to -1. So the -1 is the oxidation number of the whole permanganate ion. But now what are we looking for? We are looking for the oxidation number of the manganese. So we'll say X is equals to -1 plus 8. And then this is X is equals to 7, +7, right? So this is +7. Now that we have the oxidation number of manganese here, we can clearly see that really manganese here was reduced to Mn2+, because from +7 all the way to +2, that's a decrease in oxidation number. So we are saying this is reduced, the manganese ion here is reduced to Mn2 plus. So that means this was a gain of what? This was a gain of 5 electrons from +7 to +2. That's a gain of 5 electrons. So hope it makes sense. Then 8.2 says a standard electrochemical cell is set up as shown below. 8.2.1 says write down the function of component Y. Again, we are faced with the component Y here, which we already know is the Sol bridge. So in other words, they're asking for the function of the Sol bridge. So what is the function of the Sol bridge? So you can pick any from these three here. So these are all the functions of the Sol bridge. You can say it provides a path for the movement of ions. You can say it completes the circuit, or you can say it ensures neutrality in the cell. Either one of these will be correct. Then 8.2.2 says, in which direction will electrons flow in the external circuit? Choose from nickel to manganese or manganese to nickel, right? So now we want to know, remember, but then we are keeping the general direction that we know that electrons will always flow from the anode to the cathode. So the electron flow is always from anode to cathode. That means we must identify between the nickel and the manganese electrode, which one is the anode and which one is the cathode, right? So we're going to need, obviously, our table for that. Then, okay, we have manganese to nickel. Let me now explain how we arrived to that answer. When we look at manganese here, we can see that it is here, right? So this is your manganese ion, and then Mn2 plus, and then it gains those electrons, and then it becomes manganese. So it's up here, and then above here we don't see nickel, so we'll assume this one is the anode. And then therefore nickel has to be below because it's not above here. Let's look for nickel. There we go, we have it here. So perfectly, it's below, so that's cathode, right? So we know now this electron flow is always from the anode to the cathode. So that means it's from the manganese to the nickel, right? So from the manganese electrode to the nickel electrode. Then 8.2.3 says calculate the initial EMF of the cell, right, for 4 marks. Then to calculate the E cell, once again, we have E cell is equals to E cathode minus E anode. So what is our cathode? We said is the nickel. So what do we have for nickel? So that's a negative 0.27. Then subtract that to cathode. So what do we have as our cathode here? We have the manganese, which is a negative 1.18, right? So it's negative 1.18. Then that means we have negative 0.27 plus 1.18. This will give us 0.91 V, right? And just like that, you have your easy peasy 4 marks. So you just mainly look at this one. But then remember, with this one, with those ones whereby you have like copper there, whereby you have multiples of them, you have to check for the correct one. You don't just choose any that you see. You choose the one that has been given, right? The one that corresponds to what you've been given in the question. Then, okay, 8.2.4 says write down the balanced equation for the net cell reaction taking place for 3 marks. Now, for the net cell, let's start with the oxide half. So with the oxide half, we already identified that our anode is this one. So, but note here, whenever you are writing the oxide half, you need to inverse this. So this is Mn2 plus 2E. So if we take this one as the reactant and this one is the product, that means when you are writing it in terms of oxidation, this one now needs to be the reactant and this one needs to be the product, right? So that means how do we write that one? That's Mn. and then Mn2 plus. Why do we do this? Because we do this because we want to indicate that oxidation has taken place. So from this left-hand side to the right-hand side, you can see there's an increase in oxidation number, which clearly states that this is oxidation, right? So if you had written it in the other way around, there would be reduction, because from 2 plus to 0, that's a decrease in oxidation number. So it wouldn't make sense. So this is why we write it inversely like that, because we understand that the table that we've been given, it's actually for reduction potentials, right? But then here we are looking for oxidation. So the oxidation will be the inverse of reduction, right? So there we go from 0 to positive 2. That's an increase in oxidation number. Therefore, it's oxidation half. Now let's do the reduction half. So for the reduction half, what do we have as our cathode? We have the nickel, right? So since this one is the cathode, it's undergoing reduction, we simply write it as it appears here. So you don't change anything for the reduction half. So it's Ni2 plus and then plus 2E, and then this will give you Ni. So with this one, you can see from the left-hand side, this was 2 plus. So what happened? It gained 2 electrons, and then it became a nickel. So from an oxidation number of 2 to an oxidation number of 0, that's a decrease in oxidation number, indicating that it is reduction. There is a gain of electrons. Remember, when the oxidation number decreases, it indicates a gain of electrons, right? So do not confuse it. Then from here, since we have the same number of electrons, so here there is a loss. There is a loss. There's a, yes, here there is a loss of that 2 electrons, and then here there is a gain of that 2 electrons, so we can cancel them out. So this will now be the net cell. Let me indicate this one is the net cell. Reaction will now be Mn plus Ni2 plus. So you simply, whatever that's on the left-hand side, you write it on the left-hand side, and whatever that is after the arrow on the right-hand side, you write it on the right-hand side. Just like that. So from here, you can even see the story. From Mn to Mn2 plus, there was oxidation. From Ni2 plus to Ni, there was reduction. And therefore, you have your net cell like that, and it is, of course, balanced like that. Then 8.2.5 says the concentration of Ni2 plus is now increased. So remember, we said this one is the cathode and this one is the anode. Now, note this, because of the formula, E cell is equals to E cathode minus E anode. Whenever we increase the concentration in the cathode, we are positively impacting the E cell, the voltmeter reading, right? So whenever we increase in the cathode, we are causing the E cathode to increase, and therefore this will result in a greater E cathode, and then therefore a greater E cell. So whenever the concentration is increased in the side of the cathode, then we do understand that the reading on the voltmeter will have to increase as well, right? So if we are increasing in the cathode side, the concentration on the cathode side, then we expect an increase in voltmeter reading. But if we were increasing the concentration on the anode side, from this one, you can simply tell that if the anode goes up, then this one negatively impacts the E cell. So the E cell will have to go down, right? So that means if we increase in the anode side, the voltmeter reading becomes lower, decreases. But if we increase in the cathode side, the E cell increases. So that's what you need to know when it comes to these questions. Then the answer is increase. Now, question 8 says the table below shows 2 half cells, A and B, used to assemble an electrochemical cell under standard condition. Then 8.1 says, state the energy conversion that takes place in this cell. What is the energy conversion that takes place in a galvanic cell? We already know it's chemical to electrical energy, right? Because this one does not make use of a power source. So it's taking that chemical energy to electrical energy. Then 8.2 calculate the mass of silver nitrate AgNO3 used to prepare 150 centimeter cube of electrolyte solution in half cell B, right? So how do we do that one? We can see that here we are given the volume 150 centimeter cube, but then we know if our volume is given in centimeter cube, immediately we convert it by dividing by 1,000, right? So this becomes 0.15 dm cube. Now it is in the desired SI unit. But remember, this cell operates under standard conditions. One of the standard conditions that we know is that we need a concentration of the electrolyte to be 1 mole per dm cube, right? So that means we already have the concentration, we already have the volume, we are looking for the mass. What formula can we make use of here? It is definitely this one, the infamous one, the notorious one. Then C is equals to M over MV. Our concentration is 1, and then M here. What is the molar mass of all this? I guess it's 170. Then our V is 0.15. And then what do we have? So we have that. So if we say 170 times 0.15, what does it give us? Our mass will be equal to to 25.5 grams, right? Now, 8.3 says define the term reducing agent. What is a reducing agent? Once again, a reducing agent is the substance that loses electrons. This is a substance that undergoes oxidation. You can say that this is a substance that undergoes oxidation, but here I'm trying to like give the whole explanation even as to what oxidation means. So reducing agent is the substance that loses electrons, because oxidation is a loss of electrons. So if you can remember oil rig, we say oxidation is loss of electrons, but reduction is gain of electrons. Then 8.4, write down the name or formula of the reducing agent. So we want to write down the name of the one that undergoes oxidation, right? Of the one that loses electrons. So obviously for this one, we have to check between copper and Ag plus, which one is really the anode. So obviously we'll need our table for that. Before we answer, let's check where do we have the table. So we have we are comparing between Ag and copper. So where do we have copper? The correct copper. So we are looking for this one. And then we are looking for Ag. Ag is below here. So above is the anode and below is the cathode, right? So since copper is the one that is the anode, that means it undergoes oxidation. Therefore, our solution for that one has to be Cu, copper, right? It is the one that undergoes oxidation. Then 8.4.2 says balance the equation for the reaction that takes place for 3 marks, right? So we have already identified that copper undergoes oxidation. Therefore, when we write it in an inverse way. So this is Cu, and then Cu2 plus, and then plus 2E. So this means that this was copper with an oxidation number of 0. And now what happens as a result of the loss in electrons? Then it becomes Cu2 plus. It increases in oxidation number. So this indicates a loss of electrons. When you see the electrons on the right-hand side, that means the electrons were lost. When you see them on the left-hand side, that means the electrons were gained. So this is ox half. But then what about the reduction half? If this one is undergoing oxidation, that means Ag, on the other hand, is undergoing reduction. So we have Ag plus, and then gaining an electron, it becomes Ag, right? So just like that, we can see that Ag plus gained an electron, and then it became Ag. So we can see a decrease in oxidation number here. But then we cannot just cancel out here because the number of electrons now is not the same. So what are we going to do? Because here we have only one electron and then there too, we have to just multiply by the inverse of these numbers. So 2 here, we'll just multiply it by 1 because we have one electron here. And then we have 1 here, so we'll multiply by 2. We want to keep the same number of electrons. The reason we are doing this, we want to keep the same number of electrons. So if we had 3 here and then we had 2, we'd multiply by 2 here and then we'd multiply by 3 here so that it all becomes 6, right? So from here on, this is what we'll have. Remember, multiplying by 1, everything will just remain the same. And then, but below here, multiplying by this 2 will obviously change this. And then this is 2e and then 2ag. Now we have the same number of electrons. That means we can cancel out. So you never cancel out until the number of electrons is balanced. Then from here, you can write your net cell like this. So this is net cell. You have Cu. Whatever on the left, you write it on the left. And whatever that's on the right, you write it on the right. So it's Cu 2 plus 2Ag. Okay, we have 8.5. It says calculate the initial EMF of this cell, right? So to calculate the EMF in this cell, this is what we're going to do. So for 8.5, again, we have E cell is equals to E cathode minus E anode. Now, what is our cathode? So our cathode, we already identified that it's the Ag. And then what's the reading on the Ag? It's 0.80. And then the anode is the Cu. So where is the correct one? We have it here, 0.34. So that means now we have 0.80 minus, so it's 0.8 minus 0.34. This will give us 0.46 volts. And then once again, easy peasy max. Then 8.6 says, how will the EMF of the cell be affected if the concentration of the copper ion in half cell A increases? It goes back to what I said in the previous question. So remember here, this is the anode and this is the cathode. Now the concentration is increased in the anode. If I increase the concentration in the anode, because of my formula here, E cell is equals to E cath minus E anode, then we do understand that if we are increasing the anode, this will negatively impact the E cell. So that means the E cell will decrease, right? So the solution to that one should be decreases. Now, question 8 says the galvanic cell represented in the diagram below consists of a barium electrode dipped into a barium nitrate solution and a copper electrode dipped into a copper nitrate solution. Assume that the cell operates under standard conditions. Then 8.1 says state 2 standard conditions under which the cell operates. So we already know the standard conditions. It's concentration of 1 mole per dm cube and a temperature of 25 degrees Celsius. Or you can say, you can write 25 degrees Celsius in kelvins, which is 298 kelvins. You simply just add 273 to 25. Then you have it like that. So, or you can just leave it at temperature of 25 degrees Celsius, which we know this 25 degrees Celsius is sometimes known as the room temperature. Then 8.2, what half cell A or B is the cathode? Write only A or B. So with this one, you can see that they did not tell us which one is the barium electrode and which one is the copper electrode. So it is our duty to find out which one is the BA and the Cu. But how are we going to find out that? Remember here, they're asking which one is the cathode, right? So maintaining that the electrons will always flow from anode to cathode, we can see here that we've been they've indicated to us the direction of the electron flow. So it's all the way from here and then to this electrode. So this electrode will say this is the anode and this one is the cathode. This is how we would say electrons flow from anode to cathode. So that means half cell B is the one that is cathode. Then 8.3 says write down the half reaction that takes place in half cell A. We have already identified that this is the cathode, then therefore this is the anode. Now, how would we write the half cell reaction in here? So let's check our table here. We want to check between barium and copper, which one is the anode. So we have barium in here, and then above there is no copper, so that means this is the anode. Then where is the copper that we have? So remember, the copper that we are using is this one with the reading of 0.34. So this is definitely the cathode. It is found below, right? So that means this is the anode and this is the cathode. They're saying in half cell A is the anode. So we have to write this one, but we're not going to write it in this form because remember, what takes place in the anode is oxidation. So we have to inverse this whole equation. So this is Ba, and then Ba2 plus 2E, right? So we can see there's an increase in oxidation number indicating that oxidation took place. Then 8.4 says write down the cell notation for this cell. Now for the cell notation, remember we start from the anode. So we say the anode was the barium, it's in solid. And then what do we have in the electrolyte solution? We have the Ba2 plus ions, which are in aqueous. Then after that, we have the salt bridge, which in the second half cell, we are met with the copper 2 ions, Aq, and then they reduce to Cu, solid. So the Ba oxidizes to Ba2 plus, and then goes through the salt bridge, the Cu2 plus reduces to Cu solid. So that's how you have your cell notation. Then 8.5 says calculate the EMF of this cell. The EMF of this cell. So how do we calculate the EMF? Once again, we have E cell is equals to E cathode minus E anode. So which one is the cathode? Is the copper with a reading of 0.34, and then the anode is the barium with the reading of let's check, negative 2.90. Then let's 0.34 plus 2.90. This will give us 3.24 volts. Now, 8.6 says, how will each of the following changes influence the value of the cell's EMF as calculated in question 8.5? Write down only increases, decreases, or remain the same. They say ammonium sulfate is added in the barium nitrate solution. So this one, this is the anode in the barium, and this is the cathode in the copper. So if we are adding in the anode, what do we expect? We expect that this will decrease the EMF reading. So the solution here, we can say it decreases, right? Then 8.6.2 says the temperature of the solution is increased, right? So a galvanic cell, we have to understand this. A galvanic cell by nature is what we call a spontaneous reaction, right? And most of the spontaneous reactions, remember, we call it a spontaneous reaction because it does not need a power source, right? So this one does not need any additional heat. So spontaneous reactions are by nature exothermic reactions. So what happens when exothermic reaction, when you increase the temperature? We know that the only reaction that favors an increase in temperature is the endothermic reaction. An exothermic reaction is always against an increase in temperature. So we do understand that if we increase the temperature of the solutions here, then this will negatively impact the EMF, the E cell. So what will happen here in 8.6.2? If we increase the temperature of the solutions, because the galvanic is spontaneous and exothermic, therefore it will decrease, right? So that's the solution that we have for this one. Awesome.